The other part for this last section of quantitative data analysis is testing for the difference in results. Firstly, we have a critical value table. This is used so that a researcher can determine whether or not there is a significant difference between the two datasets. This is done by portraying a set of distribution percentiles and therefore can be compared with a previously calculated t-value. If the critical value found is below the t-value, then it can be concluded that there is significant differences between the pieces of data. However, if the critical value is larger than the t-value, then there is a significant difference within the study. As a result, a researcher must then reject the alternate hypothesis and accept that now there has been no significant outcomes. So we have the decision tree for testing for difference. So this usually is split between nominal data and continuous data or ordinal data. Nominal data difference test, so there's a couple of perhaps not as important ones, such as the chi-square test, which is intended to test how likely a distribution is as a result of chance or luck. We then have the decision tree for this, which eventually leads you down tests such as the independent t-test. So here we have the two t-tests. The t-test, the independent t-test is used when researchers testing the difference between two different groups of participants within their study, therefore acting as a parametric test because the data being assumed as normally distributed. This independent t-test uses the means to try and work out if the two sets of results can be considered to be different. Consequently, this test uses the mean as a comparison. In terms of what this equation requires us to work out, there is M1 is the main sample of 1, SD1 is the standard deviation of sample 1. In the sample size sample 1, M2 is the mean of sample 2, SD2 is the standard deviation of sample 2, M2 is the sample size in sample 2. This can be seen in the equation positioned at the top of the slide, and calculations for this equation are located within figure 20. Once a researcher has completed these prior calculations, they can go about fulfilling the equation with these values, therefore eventually producing the calculated t-value of 0.426. Then the t-value is then used in order to try and find a degree of difference within a study. We can now apply this to our critical t-value table. As shown on the slide, this alludes to a study on British gymnast and reached scores of 2 for two different groups of participants to get a critical value of 2.179, which can be seen in figure 21. Due to the fact that the critical value is bigger than our calculated t-value, there isn't a significant difference between these two groups of participants, and as a result, the meaning that the researcher would have no effect. They would have to reject their alternate hypothesis and accept that there is no change. The dependent test is also a parametric test, but is used for a study that consists of repeated measures within the same group of participants. In addition, because it is a parametric test, the distribution of data is already assumed as normal, much like the independent t-test. This test for difference also uses the mean in order to determine its results. The equation for this test can be found at the top of the slide, and like all other tests within the inferential statistics stage, there are a number of calculations that need to take place first. This can be seen in figure 22, where researchers completed these working outs on a study regarding the static and flying sprint test results for British gymnasts. These numbers can now be used to fill in the equation for this test so that the researcher can gain a calculated t-value. For example, within this example study, the calculated t-value results in being calculated t minus 0.446, which can now be applied to critical value table. Due to the fact the calculation for this df for this test is not n minus 1, the df value came out of as 5, and therefore we would look across the fifth row. Then, as the standard level of significance that we're using for our t-tail hypothesis is 0.05, we can develop the critical value of 2.571. However, according to the critical value table, this means in this case there is no significant difference between the two different sets of data within this group of participants. Therefore, causing the researcher to accept the null and reject our alternative hypothesis that there would be a significant difference within this study. Oh, sorry, I wasn't on the dependent test. This is all the values that. Sorry, I didn't realise I was looking at another one. So there are other tests such as the Wilkerson. Firstly, the Wilkerson match pair sign ranks test for the difference in a set of data by taking into account the fact that the data may not be normally distributed, therefore acts as a non-parametric test. In addition, the man-winning U is also another non-parametric test for the testing of difference within a study, and is used in order to compare differences between two different groups of participants, where obviously the data isn't normally distributed. And the chi-square test. This test is used for a piece of research where the null hypothesis is already believed to be true, and therefore attempted to indicate how likely the set of data is evenly distributed by chance. And that is the end of part 4.